My name is Ross Lockwood, and my talk today is entitled "There's Still Plenty of Room at the Bottom." And today what we'll be doing is examining the foundations of the nanotechnology revolution using Richard Feynman's life as context, because he was one of the big driving forces in the very early beginnings of the nanotechnology revolution. So the question for many of you right now is, who exactly was Richard Feynman? Why is he relevant to this discussion? Well, he was born and raised in Far Rockaway, New York in 1918. He attended the Massachusetts Institute for Technology and received a bachelor's in 1939. In this picture, he is shown with Stanislaw Ulam and John von Neumann, the famous computer scientist. And during his time there, he really developed his skills in physics. And of course, being 1939, he was recruited for the war effort, where he was actually part of the Manhattan Project. So Richard Feynman worked with Hans Bethe and Niels Bohr and Robert Oppenheimer. He led one of the computation groups that was used to calculate the yield of the bomb, the explosive force of the bomb. And in this context, the computation group is a team of human calculators. These are people whose job it is to look at a math problem and solve it, pick up the next math problem and solve it, and pass cards down a line, basically doing calculations the way a computer does, but by hand. Okay, so thousands of calculations a day would come across the desk of these calculators, and they would just solve them. What ended up happening was they tested the nuclear bomb at the Trinity site, and Richard Feynman is one of the few people who can claim that he witnessed the bomb with his naked eye. And that's a little iffy. He was actually behind the windshield of his truck, which prevented lots of the UV radiation from entering his eye and thereby damaging it. But everybody else had these little black welder's-style goggles, and Richard was like, I'm going to just watch it through the windshield. And he was fine. He's more well-known for the Nobel Prize that he earned in physics. So following the war, he turned down a position at the Institute for Advanced Study, home of Einstein, Gödel, and von Neumann, and instead worked with Hans Bethe at Cornell and later at Caltech, where he did his award-winning work on quantum electrodynamics. So this is a theory akin to Newton's laws. Quantum electrodynamics basically just tells you how subatomic particles work and gives you a framework for predicting their behavior. And very late in his life, he was part of the Challenger explosion investigation in 1986. And here he famously deduced the problem that caused the Challenger explosion, which was O-rings that lost their resilience at low temperature. And when the Challenger launched in 1986, they did it at a very low temperature that they'd never launched before at, and one of the O-rings for the SRBs became brittle and allowed hot gas to vent and thereby explode the rest of the shuttle. But he's famous for saying, for successful technology, reality must take precedence over public relations, for nature cannot be fooled. And this is just him telling you that if you haven't tested your O-rings at a low temperature, test them at a low temperature. You can only tell how the universe works using the conditions that you're testing, right? So you can't extrapolate too far without getting into trouble like this. So Feynman himself was this really tremendously great character. He's got tons of stories in his autobiography called Surely You're Joking, Mr. Feynman, where he cracks combination locks inside of Los Alamos and moves national secrets from one filing cabinet to another to scare the crap out of his superiors. And he's authored many texts that physics undergraduates enjoy today as complete treatments of those subjects. So my favorite is the quantum mechanics of path integrals. And this was actually one of his texts that we used in our advanced quantum mechanics courses here. And it was incredible. But the reason that we're here today is to talk about how Richard Feynman played into the beginning of the nanotechnology revolution. And so in 1959, he gave his famous lecture considered to be the conceptual beginnings of the field of nanotechnology. And he promulgated the idea of manipulating individual atoms and the notion of chemical synthesis by mechanical manipulation. So basically saying, if I've got If I want to make water and I've got an oxygen atom and two hydrogen atoms, I should be able to just push them together really hard and then end up with a water molecule. So his goal was to basically challenge people to do some of these things. And just to give you an idea of where they were in 1959, the first commercial transmission electron microscope was introduced in 1939. So this is a device that uses electrons instead of photons. It works exactly like a regular visible light microscope, only rather than visible light, you use electrons. And it allows you to probe deep into matter and see very tiny structures, see the crystalline structure of a lot of materials. And this is something that's also used in, for you medical students, in protein analysis. So you want to find the crystal structure of a protein, you're using an electron transmission microscope and a bunch of tools in that field. 1957, the Soviets launched Sputnik. So this is really at not only the dawn of the nanotechnology age, but the dawn of the space age. And as far as electronics were concerned, the first germanium transistor was demonstrated in 1947. The first silicon transistor was demonstrated in 1954. So this is only 5 years after the first silicon transistor. And this is the fundamental material system that all of your laptops now use. They're all running on silicon chips with transistors packed in, super dense. And so there's your final thing. In 1959, Texas Instruments commercialized the first integrated electronic circuit. So this is before you had commercialized integrated circuits. There were no transistor radios at this point, or maybe there were. Yeah, I shouldn't say that. Of course, the integrated circuit and the transistor are two separate things. Integrated circuit comes after, so I can't say anything about the transistor radio. But I can say that, you know, your digital watches and calculators, those all came after this point. And so he's talking to an audience that has not seen a digital calculator, a digital watch, any of the modern conveniences that we have. Mainframes at the time, computers at the time were still room-sized. They were using vacuum tube technology. They were basically just huge. And so there was reason for him to say there's still plenty of room at the bottom. In fact, the technology that they had at the time just pales into comparison of what we have today. Everything that we have today is thousands of times faster, thousands of times smaller. And this was the moment where people realized that you could actually do that. It was this talk. So here's a quote from the talk, and I'll read it out loud. As soon as I mention this, people tell me about miniaturization and how far it has progressed today. They tell me about electric motors that are the size of the nail on your small finger. And there is a device on the market, they tell me, by which you can write the Lord's Prayer on the head of a pin. Okay? But that's nothing compared to what he wants to talk about. That's the most primitive, halting step in the direction I intend to discuss. It is a staggeringly small world that is below, and in the year 2000, when we look back at this age, they will wonder why it was not until the year 1960 that anybody began to seriously move in this direction. Okay? Now we're past the year 2000, and the question is this statement true? They will wonder why it was not until the year 1960 that anyone began to seriously move in this direction. I contend that he was right, and that even in 2014, it's astonishing to look back and to see something that was said in 1959 that was so prescient at the time, that predicted the future, okay? So now I'm going to show you this video clip. It was originally given in 1984, but this has the same flavor as his 1959 talk. So I'm gonna go ahead. This will be the first link in the YouTube video, and we're gonna start at 0 minutes and 47 seconds and go on until 11 minutes and 15 seconds. Okay, so that's where we'll stop the video. Of course, if you're interested in the video, watch it again. Richard Feynman has a real knack at teaching people this type of principle, so it's definitely worth considering. Now, there are a couple of things that he said in there that are interesting to note. So remember, this is 1984, so this is the year of the personal computer. This is the year that the Macintosh comes out. This is the year that was predicted in 1948 by Aldous Huxley. Is it Aldous Huxley, 1984? I think so. No, that's Brave New World. Aldous Huxley's Brave New World. The other one, no, we'll fix that. For everybody on the internet, just Google 1984. So it's a phenomenally it's a phenomenally, it's a world-changing year. And Richard Feynman is saying things like, here's a commercial chip. This was done by photolithography, so it's 2,000 times reduced. You know, if you had that up on the slide, you imagine that the chip is 3 millimeters across. They used photons to create that thing. And he mentioned in 1984 that they didn't have the equivalent with the electron. They didn't have the reverse electron microscope, known today as electron lithography. And luckily, we do have that, which means we can make use of it today. But this is 1984. This is 2 years before I'm born. And we're talking about things like your computer doesn't have more than 5 megabytes, whereas now, you'd be crazy not to back up your computer onto a drive like, you know, a 2 or 3 or 5 terabyte hard drive. We've increased since 1984 a millionfold in consumer technologies, and that's just the consumer side of things. So he did talk about this in a little bit of detail, but if you do have, if you wanted to reproduce something like the Encyclopedia Britannica, of course today we'd probably use Wikipedia as the example, and you wanted to write it as small as possible, Richard Feynman allowed 100 atoms to be 1 bit of data. And he proved that all of the libraries of the world together, written in this method in 3 dimensions, would yield something the size of a grain of dust that is just on the threshold of seeing. And we can do much better today. Not only can we do this type of manipulation on much smaller collections of atoms, we can do it on single atoms, we can move single atoms, but we've gone a step further, we can actually manipulate molecular orbitals. So one of the things that I want to show you is how far we've come since this came out. Now, in 1959, when he did give this lecture, he also issued 2 challenges. Of course, this is what I like the best about science, is that when people issue challenges, right away there's people that will take up the battle. So 2 challenges. The first was to build a working electric motor that is 1/64th of an inch on a side, controllable from the outside. The second was to write a page of text in an area 1/25,000th smaller in linear scale. So this is exactly what he's basically just discussed. Can you reduce something like the Encyclopedia Britannica to something that is 1/25,000th the size? And funnily enough, the first challenge was met in the year following. And this 1/64th of an inch motor was produced by William McLellan, and it was 1/64th of an inch on a side, but it disappointed Feynman because it didn't require any new technology to produce. This guy basically used toothpicks to wind the coils and conventional machining techniques to make the components and demonstrated this motor. And Feynman, that just, I'm not going to say it crushed him, but I'm sure that he was like, why didn't I say, 128th? What he wanted to do was issue a challenge that people had to develop new technology to solve. And funnily enough, the second one of those challenges, writing at 1/25,000th in linear scale, wasn't solved, I guess, until 1985, the year after his 1984 talk. And so 25 years later, Tom Newman, a graduate student at Stanford, used electron beam lithography to write the first page of Charles Dickens' A Tale of Two Cities. And so there you see it written with each letter about, what is it? Let's say that's about 10 nanometers, so about 100 atoms across. So it took from 1959 to 1985 to get that second challenge met. But what's outstanding is that it happened before Feynman died. He was able to predict and see to fruition this challenge. And there's a couple of more interesting things about Feynman. So you know about his Nobel Prize, you know about his work with the Manhattan Project. Now you know about his famous speech. This guy was everywhere. He did a ton of stuff. And in 1983, he got involved with a graduate student at MIT named Danny Hillis, and they came up with a new computer architecture that they called the connection machine. So you can think of this in terms of a conventional computer. A conventional computer has one processor. Many of the computers that you have 4, 8, maybe as high as 16 processors. But the connection machine had thousands upon thousands of them, and they were all connected to one another, hence the name. So Hillis envisioned a computer with 1 million processors, each connected to one another with one line of communication. And so what this required was someone like Feynman to come up with these new architectures to actually produce this. Oh, did I skip a slide? I did. So there were two versions that they initially produced. The first version and the second version consisted of 2 to the 16 processors, 65,536. And they were only 1-bit processors. So they were very, very simple processors, but they were all connected together and could simultaneously perform a calculation. Since 16 of those processors fit on a single chip, they needed to produce 4,096 chips, and it was Feynman's job to come up with a way to connect the processor efficiently. How do you do network traffic on something like the connection machine? How do you get information from one point to another? So what they did is they settled on a 12-dimensional architecture with each chip connected to 12 others. And the way it looks is something like this. In the one-dimensional thing scale, you've got 2 processors connected by a line. Okay? You take 4 of those, and you put them together, all connected, and you've got now 4 processors, 4 connections. In 3D, you've got 8 processors and, what is that? 12 connections. Okay, that's not sufficient. We need to get up to 12 dimensions. So after you're done with the 3 conventional dimensions, you take each of those, and you can see kind of in the bottom left there, there's the squares, and you take every corner of the cube and connect it to the corresponding corners of another cube. So you can imagine doing this with wires, right? This is exactly how they did it in the actual connection machine. But the way that this is described in higher dimensions is by using these hypercubes. So what we have is a simplified symbolic representation of this architecture. Now we've got 8 times 2, 16 processors, and 12 times 2, 24 connections, plus all of the new connections to each of the corners, so 24 and 8 for that one thing. So we're now up to 4 dimensions. Okay, you take these guys as units, and you produce a cube out of them. This is now a 5-dimensional structure. Okay, you have to describe each processor in terms of its coordinates in 5-dimensional space. You make the sides of the cube in 6 dimensions. You've got a cube of cubes now. And you take those and you put them on corners of an even higher dimensional hypercube. There's our 9th dimensional hypercube, and finally, our 12-dimensional hypercube. So the abstraction alone is mind-blowing. Here's a simplified diagram. Each of the corners on each of the tiny cubes is a processor, and you can kind of map out how they're connected through these, in this case, you'd have to call them hyperlines. And this is actually the design on the front of the t-shirt that Richard Feynman was wearing in that famous photo. And so basically what they're describing here is how the software would run on a 12-dimensional connection machine. And the connection machine one is shown there on the right-hand side. Does anybody recognize that? Does it ring any bells, any memories? No? Okay, well, I'll get to that. So in popular culture, Feynman was a really interesting character, curious character. He was part of Apple's Think Different campaign in 1998. His family decided to sell the rights to this photo for Apple. The t-shirt itself was designed by Danny Hillis back in the 80s when they were doing it, and it describes the architecture of the CM1. So this computer allowed you to do a lot of simultaneous calculations, and all the trouble that you go through connecting all these things up lets you solve things, and in fact, in Feynman's speciality, it lets you solve problems in quantum chromodynamics very rapidly, okay? Feynman first demonstrated this by imagining what a connection machine how it might work, and then doing these calculations by hand to demonstrate that, yes, in fact, you can do these calculations on something like the connection machine, and you'd be faster than using a conventional computer, which was astounding, okay? In 1985, the first program was run, and it was Conway's Game of Life. If you guys don't know what this is, it's a 2-dimensional tile-based game where there are rules whether a tile on the grid is alive or dead, and how that evolves through time depending on the geometry of its neighbors. So I should actually show you guys a demonstration of this. If we have time at the end, I'll find a Game of Life and we can play it. And Stephen Wolfram, the same guy that wrote Mathematica and who's currently working today on some pretty incredible stuff, demonstrated a program which could calculate turbulent fluid flows. These are all really hard things to do with conventional computers because they don't have that parallelism, because they don't have that throughput, and the connection machine turned out to be really good. Unfortunately, it didn't go very far. After selling a couple of units, they went bankrupt, and there are now no connection machines in use. But I'm going to just show you this. Jurassic Park. And it's a little difficult to see with the contrast, but in the background you can see some red, and it's exactly the connection machine in the background. And here Dennis Nedry is saying, you know, anybody who can network 8 connection machines and debug 2 million lines of code for what I bid for this job? Because if he can, I'd love to see him try. Yeah, so you're kind of glossed over in the actual movie. What is 8 connection machines? But he's actually networked 8 of these, so you can think that his architecture is actually 12-dimensional plus however he did these 8 other networks. Why you'd use a connection machine to run Jurassic Park, I'm not quite sure. And in fact, in the actual book, it was a Cray supercomputer, so something probably more adept at running a park like that. But obviously, we don't blame the connection machine for the failure in Jurassic Park. We blame Dennis Nedry. So I'm going to switch tracks now, off the historical track and now onto kind of the more modern stuff. So there's still plenty of room at the bottom. This is my part of the talk. And let's just look at a comparison between the optical lithography that Feynman looked at, and this is the A7 chip, so this is the last generation of the Apple chip. Basically, what you can see is that there's an insane reduction in size. So this is 3 millimeters across. I think the A7 is about the same size, maybe as big as a centimeter. I'm not exactly sure. But the computing power is millions of times more than what this original optical lithography can do. And the precision involved in producing the A7 chip is just astounding, right? You're talking about very high frequency light, UV light, to do some of the lithography. I'm not sure if they actually use focused ion beam to make the A7. I think that they do some other tricks to get their sizes reduced. But nonetheless, you can see, sorry, what happened? We're back. You can see that we've made leaps and bounds over what was available in 1984, okay, in just short of 30 years now. So to put this in more context that you're familiar with, we have next door to us the National Institute for Nanotechnology. And there, one of my favorite researchers is Dr. Bob Wolkow. He was born in 1958, so funnily enough, the year just prior to Feynman's famous speech. He got his Bachelor of Science in 1982, again, just prior to the speech that we just watched. And he got his PhD in 87, postdoc in 87, 88, by basically solving what's called the silicon 100 structure and giving a theoretical framework and being able to model that surface. So that's just one of the crystal facets of silicon. And he's now at NINT. But he's doing some really cool stuff, and I want to show you that next. So we're going to show you a video clip from one of the presentations that Bob Wolkow has given in the last little while. And we are going to go from minute 3:11 until minute 6:11. So this is just a short 3-minute clip. All right, no one's dead, but your mind should be exploding with what you just heard. So in 1959, Richard Feynman said, wouldn't it be great if we could manipulate atoms? And he said, okay, maybe we can't manipulate atoms, but maybe we can manipulate hundreds of them. Well, this is, I think it was 2006 or 8, I can't remember exactly what date. Here is someone who is manipulating not only atoms, okay, he can pull a hydrogen atom off the surface, but their electron orbitals that are left behind on the surface. And in the example that he gave, this polystyrene reaction, basically when you remove a hydrogen, you leave a spot where a reaction can happen. It's actually more reactive to have a dangling bond sitting on a surface than anything. So a styrene molecule floating around will go and say, hey, there's a nice place to sit. And it sits in that dangling bond, you know, forms a chemical bond with the surface. And as a part of the reaction, grabs an adjacent hydrogen atom and pulls it off. So then that becomes a new site for a new reaction. A second polystyrene molecule will come in. And basically what he's demonstrated is that when you initiate one of these reactions, it grows by itself. You pull a hydrogen atom off and then leak a little bit of polystyrene into the reaction chamber, and it will grow wires for you, okay? This is automatic. And this is one of the discoveries that's going to be more increasingly important in the next 5, 10, 15, 20 years, where we're going to see actual molecular circuits coming into the world. So I've got now 2 of Bob Wolkow's animations that I want to show you next. And so I'll have the lights off for that. But I'll just give a preface to them. I've got two movies here. One is called Making a Single Atom Tip. So this is what you need to actually go and grab a single atom, right? You need to have a tip that's equally small so that you can have the dexterity to get in there and actually pull something out. And the second one is called Atom Scale Electronics. So this is the what-if scenario. We have molecular electronics. Now what can we do with them? All right, so let's go ahead and play those movies. So this is the metallic tip. This is called a field effect. What is it called? It's a electron field microscope. Yeah, I think it's called an electron field microscope, but I have to look it up again. Sorry about that. Basically, what you're looking at is the actual surface of a metallic tip, okay? And the way it works is there's a very high voltage on the tip that is grounded on the surface on a phosphor screen. And so the high voltage pulls electrons off of the tip of the needle, and they collide on the phosphor screen and let you know that there was an atom present at the location where the electrons are streaming off. So every one of those little bright patches is an electron that's, an atom that is currently giving off electrons. And the way that this process works is that there's some other gas inside here that sticks to the metal, okay, it sticks to the needle, and then rolls up the top and grabs an atom and pulls it off. Okay, so there's two effects going on. The electrons let you see the surface, but then there's another gas inside that actually pulls the electrons, or not the electrons, the atoms away from the surface. So what you get is you get a metallic tip that slowly shrinks, okay? And as it's shrinking, you can see it's also getting sharper. The number of atoms that we see is reducing. And here, this is a really interesting time. Different patterns occur, and then all of a sudden, boop, you're left with one atom left on the tip, okay? If that one gets removed, there'd be 3 down there, but the process would continue. It would pull off 2 of them and then be stable with a single atom. And this process, let's watch it one more time, Bob Wolkow holds the Guinness World Record for the world's sharpest object, and this is it, okay? And not only is it the world's sharpest object, but it is theoretically the world's sharpest object. So unless some new principles are discovered, this is as good as it gets right now, okay? And of course, probably new principles will be discovered eventually, and things will do. So what can you do with this? Well, this is the thing that he was talking about that can go and pick up atoms. And it's interesting, remember, just before it's a single atom, you might have 3 or you might have 6. Those are important too, because then you've got a patterned tip, and you could go in and pull off, say, 6 hydrogen atoms at the same time using special geometry. So keep that in mind when we watch this next video. So the next one is the Atom Scale Electronics movie, and this is also part of Wolkow's research. And I've just skipped ahead because there's some really boring stuff that goes on before it. So here we go. All right, so you guys follow this? What the tables are in this video are the actual silicon 110 structures. And what the chairs are these areas where you can actually pluck off hydrogens and create molecular orbitals. So the position of the people in those chairs was actually distribution of molecular orbitals. And this is very new research. This is very cutting edge stuff. And basically, it's showing us that not only can we get down to the atom scale, but we can actually manipulate electron orbitals at a subatomic scale and use that to our advantage. Now, they did mention that you're reducing the power consumption, you're reducing the size, but you're also reducing the cost for a single calculation to happen. Because in the case of the conventional computer, you're actually sending electrons along a copper wire to a processor through transistors. Whereas in this case, there's no charge being sent. There's no mass being moved. All you're doing is slightly shifting the atomic orbital one way or the other way. So you're actually getting away with that much reduced power consumption, because rather than, Bob Wolkow has an analogy, rather than taking a 2-liter pop bottle and filling a jug to represent a calculation being done, it's as if you've got 2 tiny little vials of the same pop, and you're just flipping them back and forth. So the amount of energy reduction in this technology is absolutely insane, but that's the beginning of it. what they were talking about when you have these dependent tiles, and this also goes back to the computing machine and Conway's game of life, but you can do this tiling on the silicon surface with these. You can see they're called dimer pairs, and you can see in the second image in A, you can see these 4 sites where the hydrogens have been pulled off, and those become the underpinning of like this quantum wire style thing. But you can use these to actually create electronic circuits. They're not simply wires. So I'll just make this one a little bit bigger so you can see. In figure B here, this is one of my friend's research projects, and he's actually designed a QCA circuitry, a matrix multiplier, okay, and there's a full adder. So these are standard electronic components that exist on typical processors. But when you think about the new iPhone, they throw around this thing where it's like the transistor size is 14 nanometers. Well, this is 0.1 nanometers, okay? This is a size reduction of about, let's say a factor of 10, but it's closer to a factor of 100 if you can really get good control over this stuff. The trouble is that this stuff is so new, you have to have incredibly sensitive equipment to use it. So we're thinking, or I'm currently thinking that in about 20 years, this might fit into your pocket, and like this method. And in the meantime, other things may come up. Other things that are currently using nanotechnology, so I'm just kind of, now I'm in the very tail end here where the lessons to be learned are that things are really tiny now. Here's a microelectromechanical system, a MEMS device, and this is the iPhone 4's gyroscope. So these innovations in nanotechnology, they're not just simply electronic, some of them are also mechanical, and you get these things, these nanomechanical devices. In this case, it's an oscillating plate that can tell you things about your position in space, right? You can have a compass module that has tiny elements. Like there are moving parts here, but they're not moving parts in the sense that they're rotating or anything special. Like these are just really cool microelectromechanical devices that give us the ability to do things like know our location and position in three-dimensional space. I mean, the whole reason that we're carrying smartphones these days is because of innovations in reducing the size of sensors and chips and lowering the power of screens and increasing the capacity of batteries. Like, all that has to happen for us to have a computer in our pocket. But Feynman couldn't have predicted that this would happen after his lifetime. So to give you an idea of the power that we're seeing from computers, so who here knows about Bitcoin? A little bit, enough to know what the word Bitcoin represents. I'll just give you a brief intro. So Bitcoin is something called a cryptocurrency. You have a coin when you have a solution to a problem, and when you give that solution to someone else, you could obviously make a copy of it, but there's something called the blockchain. And when I give something to you, we both write in the blockchain that there's been a transfer that happens. So Bitcoin is this tremendously awesome, tremendously complex system that allows you to exchange digital goods and have ownership over them using a public ledger. Okay, that's the important part. Now, to participate in Bitcoin, you do something called a hash. Okay, you're checking to see if this is a solution to a problem, right? So there's people who own Bitcoins, there's people who exchange those Bitcoins, and then there's people called the miners who find new Bitcoins. And there's many different difficulty levels so that you can't just arbitrarily find as many as you like, okay? Your computer has to solve a particular type of problem. And the problem that it solves is it looks for the solution inside of a particular block of numbers, okay? It's kind of like, it's peer-to-peer currency exchange where the people who are doing the mining are also the ones writing the ledger. Insanely complicated, very cool. It would take an entire lecture to give you a flavor of understanding it, and even then, you would probably need tremendous, you could write whole courses on how Bitcoin works. It's insane. So this blockchain technology, next time you're browsing your feeds and you see blockchain, you'll see it more and more because this is useful not just for exchanging currency online. Right now, to mine a Bitcoin, only 1 out of about 1.4 times 10 to the 20th hashes are successful. Okay, you guys are doctors and business people and biologists. The biologist probably has the best idea of what that number represents. But 10 to the 23 is the number of carbon atoms in 12 grams of a powder of carbon, okay? So there are a tremendous number of atoms in just like small quantities. This, 10 to the 20th, I mean, it's hard to even fathom how big that is, but that's all you need to know right now. To mine a Bitcoin, you have to do approximately 10 to the 20 hashes to find a solution to the Bitcoin problem. If you do that by hand, one hash, a single round of the SHA-256 algorithm, would take a human 16 minutes if you just wrote this down on a piece of paper. Now imagine to find a Bitcoin, you have to do that 10 to the 20 times. So right there, that gives you an idea of how good computers have gotten these days. But I'm cheating a little bit. These aren't conventional computers. For Bitcoin mining in particular, they have these things called ASIC chips. These are application-specific integrated circuits. And in the case of the one that I'm showing you here, Butterfly Labs 10 gigahash per second Bitcoin miner, this thing has a chip that is optimized for doing the hashing process. So that thing that you saw written out by hand, that is hard-coded, not hard-coded, hard-baked into the actual hardware. The actual transistors that are patterned on the surface can do that so efficiently. So 10 gigahashes, how come I can't see my notes? I'm gonna have to just exit for a second here. I'm gonna say this out loud. So at 16 minutes and 45 seconds per one round of hash, a human does about, it takes 16 minutes, okay? For an ASIC chip, you're doing one hash in about, I didn't do that calculation. Anyway, the point that I'm trying to make is that the ASIC chip is about 10 to the power of 10 times faster than a human, okay? To do what the ASIC chip can do in 1 second would take a single human over 320 years, which is 1.3 times the orbital period of Pluto, and about 11 generations worth of human beings. So your great, 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 great grandson or granddaughter or whatever they invent in 11 generations would not be able to beat a chip from today, okay, at doing these hashes. In 1 second. In 1 second, this chip does what your family would have to work on for 11 generations, okay? And the funny thing about this is that at current prices, you can get this for about 50 bucks. So 11 generations worth of work down to $50, and you plug it into your wall, and then the cost that it takes to power it is the upkeep. Now, out of curiosity, when you're running one of these, you make about as much money as you spend on the power it takes to power the device. So when you do happen to find a Bitcoin, it might be worth $100, but you've been running this thing for about $100 worth of electricity, all right? So right now there are some economic forces at play that maybe make you not want to buy this. So this is the application-specific integrated circuit, and of course, there are other types of computers out there. We talked about the connection machine, the conventional computer. We talked about application-specific, but what about quantum computers, okay? This is outdated by a year, so it should say 2 years ago, D-Wave, a Canadian company, installed D-Wave 2, this is their second generation, in the Quantum Artificial Intelligence Lab, a joint project between NASA, Google, and the USRA, and Lockheed Martin bought one, okay? And this is kind of the beginning of a new era of computing called, well, of course, quantum computing. This computer is arguably not a quantum computer. It's using a method called adiabatic quantum computing, which some theoretical physicists would argue is nothing close to what a real quantum computer can do. And the demonstrations that they've done with this thing, of course, it solved Sudoku very quickly, but the problems that it's optimized for are the same kind of problems that the connection machine was really good at. So any of these ones where you've got this vastly connected system, like air molecules bumping around the airfoil of an airplane, that's why Lockheed Martin purchased the upgraded system. It can do calculations that a conventional computer would take a long time. So think about the quantum computer in terms of our human to our Bitcoin miner analogy, okay? What a conventional computer can do might take 11 generations. A quantum computer could do it in a fraction of that time. And we're only just beginning to see what kind of performance improvements we get. Of course, quantum computers are very specialized right now. You probably won't see them in your cell phone in 10 years. But come 10 years, who knows? There might be a little quantum module in there that can calculate the local weather nearby and tell you if it's going to rain on you. Who knows? I'm going out on a limb on that one. But there's one thing in common with all of these things that we've seen so far, even the connection machine, is that every single one of these chips was done on an area. Okay, Feynman talked about, if you wanted to write it on the head of a pin, you're reducing the area by about 40 million times. But if you use the volume as well and make it into a cube rather than a flat surface, you're getting a tremendous leap in performance, right? You go from the head of a pin to a grain of dust that you can barely see. And there have been some attempts to do three-dimensional architectures. Intel's Pentium 4 chip was based on 3D architecture, and they were experimenting with, just 1, 2, maybe 3 layers. But I think the Pentium 4 had 2 layers. And of course, more recently, Samsung's VNAND SSD have 24-layer structure, doubling the number of transistors per square millimeter. So again, the first halting steps in the direction of making things in this three-dimensional architecture. Of course, you have problems of heat dissipation and all sorts of other things, like how do you connect to something deep inside of this structure? How do you read out memory from a structure like that? But that's the direction that we need to go. You guys know, probably by anybody who's recently bought a computer, that you're getting, at a max 3.8 gigahertz chips, okay, which isn't a tremendous leap from 10 years ago when the first gigahertz chips started coming out. We didn't see the tenfold increase in the last decade that we've been used to, and that's because we've almost run out of space in which to shrink conventional computers in area. And now we're really starting to see people go and look at the three-dimensional aspect. So what could those possibilities be? Well, a good candidate is the diamond NV sensor. So if you take your standard diamond ring and you knock one of the carbons out and replace it with a nitrogen atom, you get this thing. Well, you don't necessarily replace it with a nitrogen, but you can see here there's a nitrogen, there's a carbon, and then there's this thing called a vacancy. And the vacancy is very similar to what the dangling bond was that Bob Wolkow was talking about. But basically, you have a place where there is no atom, and that thing has properties. So people are at the moment trying to figure out how you knock out these vacancies in an ordered array. Right now, it's very difficult to get inside of a diamond and knock them out. And I think the solution to this is to be building this structure layer by layer. You do first, you start with a layer of graphene, and then you pull out the atom that you want to be a computational element, and then you put another one down, and somehow, and this is the magic, this is where people still have room to figure things out, you take another layer of graphene and you squish it down, and you make the bonds between the appropriate carbon atoms so that that becomes a diamond structure. Okay, then you pull out the right atoms for the next layer, and you take another sheet of graphene and you lay it down, and you could build up a computer in that way. But that is, again, looking a little bit forward. With this being the end goal, so Computronium is a theoretical arrangement of matter that is the most optimal possible form of computing device for that amount of matter. So you can imagine that to go back to Feynman's analogy, you could take all the libraries of all the world and fit them into, what did he say, a few inches on the side? What if you could do that with all the computers in all the world and fit them into a similarly sized cube? And that is kind of what Computronium is. And then, of course, you run into this classic computer science problem. What problems should you solve? Okay? And that's where medicine comes in. That's where protein folding comes in. That's where designer drugs come in. That's where genomics comes in. Okay? So when I see you guys again in 3 weeks, we'll be talking about the promise and perils of nanotechnology. Okay, so what exists on the market today, what people fear about nanotechnology. That's one of the big concerns, is that nanotechnology is somehow outside of the limits of what humans can control. And with that, I'd like to open up the floor to some questions. Hello.
Hi. I'm just wondering, so how far is the software by catching up to the hardware? So I think there is software for quantum computers, but I don't think they're advanced enough, like you said, for commercial use. And
sorry, I'm missing the very first part. So
how long is it going to take for the software to catch up?
So
to all these
yeah,
advances?
that's a good question. Software and hardware, where do they meet, basically? Now, when it's something like that application-specific integrated circuit, there's no software involved. You literally interface with the hardware. You plug this thing into your network and power, and it just starts crunching. It's got everything basically baked in. Of course, there's always like a little operating system that controls it, but as far as that chip is concerned, when the software asks it to do a hash, it basically gives it a string of numbers on one side of the chip, goes through whatever number of hashes it needs to, and then on the other side of the chip spits out a number. So in that sense, there are computer chips that require no software whatsoever. They are basically on their own. And you'll see probably more and more of these application-specific integrated circuits in the future. Right now, we're kind of undergoing what's called the microcontroller revolution, where you're seeing things like Arduino and the Raspberry Pi and these little $40 computers that you can plug into your TV and have a little terminal on your TV. Like they're everywhere now. And that's the foundation for the Internet of Things. So on the top end, we've got the Internet. And on the bottom end, we've got the hardware that it runs on. And they're all getting smarter simultaneously. I don't think that one is outpacing the other or anything like that. But what we're seeing is that when new hardware comes out, right away people are rushing to write new software for it that uses the specific advantages of that. So we're seeing chips like the IBM, is it IBM? The Intel Edison, which is about the size of an SD card, and is about, I think it's about a 300 megahertz processor in there. So it's about as good as a computer as I had back in 1996 on an SD card, okay? And the goal of that, you connect wirelessly to the internet. So you've got this little computer that you could stick anywhere you'd like, put a sensor on it, give it something to do, and it will just happily run and do that thing for you. So you could imagine, you know, right now we're seeing lots of home automation applications for those types of computers. But to answer your question, I think as best as I can is that software and hardware are really on par with each other. New hardware comes out, new software comes out. Quantum computer, adiabatic, whatever comes out, there's always going to be someone ready to use that hardware. Maybe not to its full advantage, but then again, like to that hardware's generation's full advantage within 3 to 5 years.
Yeah, because can't you also use software to get the same results as like nanotechnology to compress files while keeping the same quality? So
yeah,
in
and
the
that's,
end,
well, you can and you can't. Of course, there's some limit to what you can do, right? For a single-threaded computer, the software can make one request at a time and then wait for an answer, right? When you're talking about a connection machine, you can ask a lot of questions simultaneously and get a lot of answers simultaneously, but it's limited to the computer hardware that you're asking it. So there's never going to be a trick in the software that will allow a processor to do what it's designed to do faster. Okay, that's a limit. But this is why mathematics is a very fruitful field to be in. You can always discover a faster way to do the calculation that you want. Remember, like, when you're learning how to do, I don't know, what's a good example? I mean, I'm a physicist, so you're trying to calculate the velocity of a wave on a string, for example, okay? You could just watch the wave, or you could measure the tension in the string and how heavy the string is, and then do a calculation to see what the velocity is. So like there's that kind of shortcut where sometimes the problem is hard to do one way, but if you apply math to it, it becomes easy. And the converse is true too. For some computers, some types of problems are easy and some types of problems are hard, and it's the software layer that decides how the hardware implements it. So do you do the very hard computation over a long period of time, or do you break it into smaller, easier to do problems and then do, you know, very simple calculations to get your result? So there's a trade-off, right, in terms of
yeah, and also I'm just like, in terms of just space,
yeah.
like you can make different file types, right? Like for images, for example.
Yeah, and that's kind of a compressibility theory kind of thing. So yeah, you can definitely use hardware to certain advantages, but in addition to there being fundamental limits of hardware, there's also fundamental limits of software. So you know, there's plenty of great theorems that say if you have a certain type of data, you can reduce the size of this data by using compression algorithms to this amount. But then there's laws that govern what the smallest is that you can do that for a given input, right? So there are limits both in software and in hardware. It's not infinitely solvable. Of course, now you're really getting me going, and it's like, I always envision that, physicists are often talking about these compressed, these rolled up dimensions. What if you could somehow sneak information into one of those compressed dimensions and do a computation in there and then pull it back out? Right? You've not altered anything in real space. So the question becomes, can you somehow use these higher dimensions that are theorized but not yet conclusively proven to run a calculation? Can you somehow like slip your computer out of the universe? Okay, it's gone. Okay, time is running here. Maybe time runs faster outside the universe or wherever you stuck this thing, and it finishes its calculation and you bring it back in and you go, wow, what would have taken me 3 billion years to do only took 1 second because I have this clever way of somehow sneaking my computer out of the universe and then pulling it back in. That's super crazy, and I realize that, so don't email me to say that that's crazy. I understand it's crazy.
I was wondering if most of the research that's being done in nanotechnology is done in private companies or if it's done in universities.
That's a good question. I was actually thinking about this earlier today in terms of like, Gaussian distribution, right? Like we've got consumer electronics at the center of the Gaussian distribution. This is your iPhone, your iPad, your Microsoft Surface, your Toshiba laptop. They all fit into like, the general average consumer device. And then you've got the first sigma towards the high-tech end, right? And that's your power user devices like this Bitcoin miner ASIC chip and, the Mac Pro, something that a normal person wouldn't probably buy, but someone who's doing computer graphics and rendering and stuff would need something like that. And then you've got your 2 sigma, and that's the commercial companies that are using to manufacture these devices. And that 3rd sigma away from the center, that's where the research is taking place. And of course, we have things like the National Institute for Nanotechnology, and there's the research park down in South Edmonton that does, they do have companies doing the research. So I couldn't tell you because I have no idea. Companies don't tend to reveal what their research is. They like to keep it secret. Intel's not out there writing papers to say, here's how we improved electron lithography that allowed us to produce, the next 5 nanometer transistor that will be in your iPhone. They're not apt to do that because that undermines their bottom line, which is to make money off of these things. But you can look in the literature and you can see just how diverse nanotechnology as a field is, because it's not really a field per se, it's an extension of all the existing fields. Biology, chemistry, physics, even geology, they're looking at smaller and smaller aspects to get material properties and stuff like this. So, when you see nanotechnology on a package, and like an example that's been discussed to death are the socks that have silver nanoparticles that are antimicrobial. Okay, does that really constitute nanotechnology, or is that just using really tiny things, right? The silver nanoparticles in this case are nanometer size, but do they constitute nanotechnology, right? So I'm doing a very poor job of answering your question, but I hope that you're getting something out of it. Basically, the question is, what is nanotechnology? And so I think of nanotechnology more in terms of the computer chip than I do the antimicrobial aspect. But very clever people now are producing nanoparticles that have selectivity, specificity to do certain jobs. And that, by all means, is nanotechnology, right? If you have gold nanoparticles that you coat with a cancer-detecting protein, and they go to that site, and you can then microwave it because you've got gold nanoparticles in the site, like that is essentially like bio-nanotech right there, exactly what you want to do. But especially genomics, that's where you're going to really see humans learning about molecular machines and being able to reconfigure proteins for better purposes, right? You'll be starting to see, of course, self-repair is big on the list of genomics. People want to produce bacteria that are super efficient at converting sunlight and carbon dioxide and water into ethanol so that we can all drive ethanol-powered cars. Of course, there's battery technology that goes into future electric cars and hybrid cars and everything like that. So nanotechnology is a messy word because it's such a broad word. It basically covers everything that's below a certain scale. And then you get all sorts of other people debating what the definition should be. Should it be something that has active properties where it goes and does something, or is it okay to call something nanotechnology if it's passive? I mean, if it fits into the passive definition, then like my water is nanotechnology because each of the elements in my water model is an oxygen atom with 2 hydrogen atoms. So you get into this strict debate about what nanotechnology is, so it's hard to answer that. But of course, I don't think that you can really know. You can look at the budgets, R&D budgets of universities compared to, say, Intel, and try and understand what that's what those numbers mean in terms of their like research output. But Intel's never going to hand you the keys to the kingdom and tell you how they did it.
So do you think the ethical implications of nanotech will limit it, or do you think the ethics will move with it?
Yeah, we're at a point right now where the ethics is definitely lagging behind, but I think that that's a result of not having a lot of ethical issues crop up. Like in general, if you're doing studies that involve humans or biological tissues, you're seeking permission from your faculty and the institutional review board for ethics permissions, right? So for the most part, the universities that are doing this research are being held back, right? They're being reined in by ethics committees. But then you get into strange areas where you're not doing human testing. So, you're basically free and clear to, actually, I should actually show you guys something. I just emailed this out right before I came here. Let me dig it up. So, super secret. Cut this out of the video. I'm going to just open this up and drag it over here for you. Yeah, I got an email. So I just got this data this afternoon, and what I did is I coated the tip of a fiber optic with some quantum dots, and then I pumped argon through the system, and at the 30-minute mark, I added argon plus 1 molar vapor, well, it's not 1 molar vapor, but 1 molar solution where the vapor is being passed through it of nitrobenzene, which is an explosive / an explosive marker. So when you manufacture explosives, you add these tracers in them. This is what you actually detect at the airports. You're not detecting the explosives, but for commercially manufactured explosives and for commercially available materials to make explosives, they sneak in little signaling molecules, and nitrobenzene is one of them. So if you can detect nitrobenzene, you can be pretty sure that it was carried there by something more sinister like TNT or something like that. But this just goes to show you that I didn't have to get an ethics review board's permission to do this, but in a sense, because the sensitizing elements here are silicon quantum dots, it is nanotechnology by all means. It's just that I'm not harming anybody by doing this, not even myself in this case. You get into some ethical debates now. You talk about Marie Curie. She didn't know that she was getting radiation poisoning slowly over her entire life. And I mean, we have a better understanding of the fundamentals of matter now, so we're pretty sure that we're not getting some strange like nano rays that are going to cause cancer later in life. But you get the idea that there are unrestricted areas of nanotechnology research where if it doesn't have ramifications for interfering with biology, then you basically get a license to go ahead and do it. Now, with that being said, this, of course, is a great introduction and prelude to the lecture in 3 weeks, Promise and Perils of Nanotechnology. So we'll get into that a little bit more, and in the next 3 weeks, I'll make sure that my brain is tuned to some ethics stuff in nanotech so that when we get back to this topic, I can answer it in more detail.
So I think that we're out of time for today. We haven't ever had a break like the break we're going to have. Our next class will be on the 21st, and the next professional videography will be on the 23rd. I was just kind of reflecting about the fact that there's probably no going back now. There was always this idea that, if there was a nuclear war and only few survived, that all the technology that we know would be gone, right? and the idea of bombing them back to the Stone Age and so on. Now you get the idea that could not occur. If there was a nuclear war and only few survived, they'd have smartphones, right?
Yeah.
And even if there was no internet, now they'd have peer-to-peer communication somehow using those phones. They'd find a way to power them. And in this way, I sort of differ. Michael Whiteside, when he gave these lectures, would always emphasize that with increased complexity, you get this very fragile system, that it becomes more and more fragile. And what I would argue in some general way is that the technology that we have today is so robust that it would survive almost anything, you know?
I'll speak to that. I know you guys probably are itching to get out, so I won't speak too much, but I like to use an analogy of, like, what do you leave behind when you're a Stone Age person? You leave behind your stone tools. And when I find that and I go, there's a sharp edge on this side, I can deduce that the sharp edge was used for this. But what happens when someone at the level of the Romans, technological proficiency of the Roman, goes and finds a USB stick, you know, thousands of years from now? Right? Are they going to know that I can use this USB stick to extract information? The problem isn't storage, it's retrieval in that case. Mm-hmm. And right now we're in this very fragile age where retrieval is a problem. My laptop completely died on me on the weekend. And if you guys don't do backups, do backups. I have plenty of backups. I've got them stashed all over the place. So, you know, I'm one of these people that digital archaeologists will go, man, this guy was cool. He had backups from here, and they'll be able to have all sorts of forensics based on which backups are older and cool stuff like that. But I had to restore from it, and even that was a challenge, right? My computer now is running most of the data that I had and most of the programs that I had, but even the process of restoring it with current technology that's designed to be restored, I had issues. So then you're talking about, you know, what does the Roman do when he finds a USB stick?
Right, but you know, if you just think, you know, the military's influence, for a long time there's been this problem of, you know, if you had a disk from 10, 20 years ago, could you read it? Now, you know, the military has this 100-year archival disk that's guaranteed to, you know, maintain stuff and to be readable. Why them? Well, you know, that's sort of the way it is.
Yeah, maybe I'll touch on that, because there's librarians call it bit rot. Even if you have it stored safely, securely in a medium that you trust for the next few years, there's no guarantee that a cosmic ray isn't going to go through and flip one single bit, and that bit might be the linchpin for reading that file, right? It might say, it might have the header information for what file type that is, and then you can no longer tell what file type it is. So you either have to do forensics, or you have to say, I don't know what this is, I can't read it. Because data, if you just look at it from, you know, a zoomed out, the forest view, just looks like random garbage.
Right. Okay, thank you very, very much, and I'll see you guys on the 21st.